All right, let's see if you got those answers correct on the last Test Yourself from the Orbital Shapes and Diagrams video, and hopefully you did get them right. So the Test Yourself was about sulfur, and there were quite a few parts to this, so let's take our time and go through the answers for each one of these subpoints. First, we're going to write the long electron configuration for sulfur. As always, we need our periodic table handy and ready to go so that we can locate where sulfur is on the periodic table. The long electron configuration always begins with 1s, so we're going to start with 1s and begin reading across. We have 1, 2 to get out of the 1 level, so we're going to write 1s2. Now we're down in the 2 level, so 2s block over here. We go over 1, 2. Then we pop over to the P block, still in level 2. So this would be 2P, and we go over 6 to get out of that level entirely. Remember, sulfur is here. That's the goal. That's where we're going. We need to start back over here, just like when we read a book, from left to right, top to bottom. So we're going to go to level 3. Again, that pops us back over into the S block, and we go over 2 to get out of the S block. And we're going to drop over here to 3 levels still, and we're going to count in the P block 1, 2, 3, 4 until we get to S. So that would be 3P4. Excellent. For our short electron configuration, we're going to look back at the previous noble gas before sulfur. So if sulfur is here, the noble gas that's right next to it is argon. We don't want that one, we want the one before it, which is neon. So we're going to write neon in brackets below and start our reading frame from neon. Then we're going to jump down to level 3, S2, 3P4. So essentially we're just taking this part of our long electron configuration and writing it next to neon, disregarding the beginning part of the long electron configuration. Now we need to determine sulfur's valence. The valence is determined by the highest shell, the highest energy shell. How many electrons are in that highest level? Our highest level here happens to be 3, and there are electrons in the exponent, so that's our 2 and our 4. So we're going to add 2 plus 4, and that'll give us a valence of 6. Now to figure out what charge sulfur will make if it were to become a charge, we need to use the octet rule and determine how far away is 6 from 8. It wants to be like a noble gas. So either we can gain 2 electrons and become like a noble gas, because 6 plus 2 would give us 8 for an octet, or the other option would be to lose 6 electrons. Just like human beings, these atoms are going to take the path of least resistance, and sulfur is going to choose to do the thing that's easier. In this case, the thing that's easier would be to just gain 2 electrons, then lose 6. If you gain something that's negatively charged, if you gain negativity, i.e. an electron, you become -2 charge. You gain 2 negativity things, 2 negative charge. So in this case, the charge that sulfur would make would be S -2. What would sulfur's orbital shapes look like? For orbital shapes, we need to draw a Y, X, and Z axis. X, Y, Z. Now we're going to take our electron configuration and translate that into one big mess. We have 1s, that's a sphere, that's small. We have 2s, that is a slightly larger sphere that encompasses the smaller 1s sphere. We also have 2p. 2p is shaped like a peanut, and it's going to be the same size as the green sphere on the x, y, and z axes. So it already looks pretty nasty at this point. It's going to get better. We have 3s, that was sarcasm by the way. We have 3s, that's a slightly larger sphere that's going to encompass everything now, just like that. And we also have 3 P4. So with 3P, we're looking at peanut again, that's bigger, so it's going to be the same size as the purple sphere on the Y, the X, and the Z axes. That would be my orbital shapes. That's what it would look like at an atomic level if all of our orbital shapes were present for sulfur. Now we want to write the orbital diagram. That's what OD stands for, not overdose. It's orbital diagram with the boxes and energy arrows for a neutral atom. Sulfur, when we look at the periodic table, has a number of 16. So that means we have 16 electrons to fill in an orbital filling diagram. An orbital filling diagram should be drawn. Let's get rid of that gobbledygook here. We can actually get rid of this too now. And let's draw our orbital filling diagram. We have our energy arrow. We have a 1s box, a 2s box, a 2p box, a 3s box, a 3p box, a 4s box. Okay. Now let's fill it in for the number of electrons that sulfur has, which again is 16. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So that would be my orbital filling diagram for a neutral atom of sulfur. Now if we were going to write the orbital diagram for the charged atom of sulfur, remember that charged atom is S-2, so it's easier for it to gain an extra 2 electrons up here in our orbital diagram. Notice that it's all filled now. So once we were going to draw a filled orbital diagram, all we'd have to do is just add those extra 2 electrons in those boxes, and voila, we are done. Bada bing, bada boom. It is over. Now, if we wanted to tack on one extra question here, we could also write out the electron configuration for the charged atom of sulfur. So the charged electron configuration would be our 1s2, 2s2, 2p6, 3s2, 3p6. Now remember, when we're talking about the electron configurations of charged atoms, they're wanting to be like the noble gases. So in this case, if sulfur gains 2 electrons, it ends up becoming like argon. So technically, this electron configuration is the same electron configuration that you would see for argon, because that is who sulfur is trying to be like when it gains 2 electrons. Hopefully you got all those answers right. Wishing you a quacktastic day.
No ducks, no glory.